Good morning. My name is Julie Uval, and I'm the Senior Marketing Coordinator for Beck Technology. We're excited to welcome you to today's webinar. This is our second in our series on innovation in the AEC industry, and we are joined by Martin Fischer, Professor of Civil and Environmental Engineering and the Director of the Center for Integrated Facility Engineering, or as most of you may know it as CIFE. As many of you know, Stanford is one of the leading research universities in the country, if not the world, and CIFE, in our opinion, is the leading applied research program. We have been a member of CIFE for many years and have worked with students and faculty at CIFE. We are honored to have Martin join us today to provide a little more insight about CIFE and the research he and his team are conducting with member firms such as Beck. You do have the option to ask questions via instant messenger on the GoToWebinar, and we will save some time towards the end of the program to ask Martin those questions. Without further delay, Martin, please take it away.
Good morning, everybody, or evening, depending on where in the world you are calling in from. Thank you, Julie, for the introduction, and thank you, Beck Technology, for hosting this webinar and also for the support over the years and the collaboration. Because I think it is through this kind of collaboration between universities and companies and also government that we can advance our industry and serve our clients and society better. So that's what I hope to show you in today's webinar. So let me start by sharing what I see as good practice in terms of designing and managing building projects. This is from one of our member companies, Optima, a developer in Phoenix and Chicago, one of their recent developments in Scottsdale. This is actually a few years old, and you can imagine that they have advanced since then. But they, on this project, which opened a few years ago, were able to leverage building information models for overall coordination, system-level design, constructability, coordination of the MEP systems, of course, construction simulation, detailing, quantity takeoffs, estimating, sunlight studies, and various kinds of analysis to determine what exactly is, in this case, the best planting scheme for that development. These tools were extremely helpful for Optima to bring this building to market sooner and with higher quality, which, given that they were able to get this done right before the financial crisis, was of vital importance, basically led to the survival of the company. If you go to that intersection there where Camelview Village is, which this development is, you see right across the street a developer who was not quite as fast, missed the market window, and went bankrupt. So these tools can have a really big impact on our work and the success individually and on the project and at the company level. So this is what we have really worked with our member companies over the first 20 or so years of our existence to make happen. And what I will present today is a glimpse of what I see as best practice in using building information modeling, virtual design, and construction methods, and then what we're doing on the research to move this field further. Because as we had our annual advisory board meeting a few months ago, we asked our member companies whether they want our help in moving virtual design and construction practices further into their business environment, or whether they want us to work on what Jeffrey Moore calls the next chasm. And they very quickly said we should focus our attention on the future, what comes once building information modeling and virtual design and construction is truly the established practice. So that's why I will show basically where I see the leading companies are being today and what we are doing to make that even more productive. So just a quick background on the Center for Integrated Facility Engineering. It has existed since 1988 and has been and has to be 100% funded by industry. We have companies from the building owner side, from design and construction, and then from software and hardware vendors for our industry. If you had visited us in the 90s, we would have talked your ear off about the potential of building information modeling. Over the last decade, we have focused on bringing building information modeling into practice, making it a method of designing and building and also to some extent operating facilities, which we call virtual design and construction. And now we are really focusing on breakthrough performance, integrated facility engineering, as you will see when we talk about our research. So in a nutshell, all of us are part of this cycle of innovation and improvement, and obviously it's only through innovation that we can stay in business and enhance our standard of living. Obviously the companies have the practice piece. You build the projects, you design the projects, you operate the buildings. We carry out research in the context of what we see as best practice with our members, like for example BEC and BEC technology. We identify potential areas for improvement from problems in practice or from opportunities created by advancements in, for example, computer science. Then these research results go, of course, back to practice, but they also flow into our educational offerings. And you can then hire our students that know how to work with these new methods. And that leads to an advanced next best practice, which then gives rise to the next cycle of innovation through research, education, practice. So all of our research happens in the context of actual projects with our member companies. I think together we can go through this cycle of innovation dramatically faster than any one of us can do on our own. We couldn't be successful just working on our own at Stanford. Similarly, we believe that the companies we work with could also not go through this cycle as quickly as we can do when we work together. That's really what the CIFE community in a big picture level is trying to do. So let me then focus on a couple big trends that I see have the potential to truly disrupt our way of working. Or we can also see it as a big opportunity. But one of the wake-up calls I got a couple months ago is related to this point here. So how much do you want to earn per hour? Typically the answer I get is, $100, more than Bob over there. Sometimes people say that's not quite the right question, which I agree with. But nevertheless, we should have some value for what we make per hour. And so the question is, do you want it to be more than 11.9 cents? And of course you say, well, yes, Martin, please, we need to make much more than that. Well, why do I say 11.9 cents? Is that at least the market rate we got for buying an hour of computing in the cloud is 12 cents. So this really brought home to me that computing is now virtually almost free. And that means that I have to be really careful with respect to what I do and what the computer can do. And I think in our industry, we still have a big potential to let the computer do what it can do well at 12 cents an hour and then free us to do things that we are good at where the computer is not yet good at, that are much, much more value adding than many of the things I see us doing on projects day after day. Because I am certain that somebody in the world will figure out how to use this 12 cent an hour resource well, and I'd rather be part of that team than the team that has to compete without this 12 cent an hour resource. Another big trend is, of course, the availability of data. In our building, if you come and see us physically, we are have been collecting for 4 years 3.5 million data points per day on its performance. Every minute we collect 2,400 data points. And the Microsoft facilities, for example, on its Puget Sound campus collects 500 million data points per day. So if we think we are drowning in data today, that is really just the beginning. So again, obviously, there is tremendous information and insight in these data that we need to figure out how to harness. And again, somebody will figure out how to do that, so we might as well be part of that team. A third major trend is that we do have to dramatically change the impact of our facilities. I mean, this is just a pretty ironic ad that I found a few months ago by Humble Oil, which later became part of Exxon, where in 1962 in a ad in Life magazine, they boasted that they are creating enough energy to melt 7 million tons of glacier. Yes, no kidding. So obviously we have to change that trajectory that we're on. Otherwise our kids will be swimming like that boy in China. which I don't think we would like to have happened. But the trajectory is very dramatic. We are on an upward trend on CO2, and we need to totally reverse it. So to sum up, we can see a number of dramatic trends, I believe. Computing is almost free, and of course mobile data are abundant. That's sort of drivers from outside our industry. We have developed a business practice that I would sum up as what you see is what you get. That's certainly feasible today, as you saw in an example up front. And we also need to not only meet first cost and budget and budget and schedule on our projects, we need to now make them demonstrably environmentally and socially more sustainable. And I've noticed, certainly in my travels around the world, that the world is flat, because I see the same challenges, opportunities in Cairo, in Hong Kong, in mainland China, in Europe, wherever I go. And all of this is normal for today's high school students. Why do I make this point? Is that in a few years we want to hire the bright, creative kids from that generation. And this is the normal world for them, but I don't see it the normal world for us with experience in construction. So I think this is more of a challenge for us than the high school students, for us in terms of attracting the creative, creative, smart minds from the next generation of construction leaders. So at the end of the day, we still have to deliver a project that is buildable, that can be operated efficiently, that makes the users of the facility productive, and enhances its environmental and social context, and hopefully also that contributes to learning how to do the project even better next time. I think we all strive to achieve that on a project, but don't always quite get there. And I think the reason is that, again, we all strive to have a high-performance building. And we don't, I would say, if you allow me to say it so directly, I don't see many project teams that have a very clear strategy to achieving this high-performance building and implement it successfully over the life of a project with the choices they make with respect to design, organization, and process. Because how would we recognize a high-performance building, or what will make a building high-performing? I would argue it's a building where the building systems are integrated, meaning where the product elements, the mechanical system, structural system, facade, etc., work in concert to support the purpose of the building. I would think that such a building would be more high-performing than one where these systems are separate. Then how do we get one of those integrated building systems? I think we have a better shot at getting a building with integrated building systems through integrating our design and construction processes. Because it's difficult to imagine how a set of fragmented separate processes can lead to miraculously an integrated building system. So how do we get then this integrated process? It's by integrating our team, the organization. Because again, if we keep everybody at arm's length, keep them separated through contracts, it will be difficult for them to carry out integrated processes, and we've already established that that's vital to getting a high-performing building. So how do we get this integrated team to work? I believe a key mechanism is to have integrated information, BIM plus, as I call it, you could also call it, because if the team has to work for the information instead of the information working for the team, it's again unlikely that they can put enough attention on the appropriate collaboration to create this high-performance building. So you can see how important I think integration is as a strategy to complement the well-established divide and conquer approach that I find on most projects, and that is sort of established project management practice. Of course, we have to, so key mechanisms, I guess, to support the project team through this integrated set of information is through simulation and visualization. There's a number of techniques, methods to support the collaboration of the integrated project team and allow it to carry out the integrated processes, including collocation, method we call AEC, Integrated Concurrent Engineering, which we borrowed from Jet Propulsion Laboratory. Then production management, lean, construction management, those techniques are critical to establish appropriate processes that are most effective and lead to the right product decisions. And then, of course, we have to define what the building should accomplish. What would a high-performing building really mean? What's its purpose? What are the values of the users, for example? What are the performance metrics that we should have so that we know that one building design is better than another? And it all has to be supported by some form of agreement, a framework that allows each of us to work on this team and be successful individually and in our companies. We see the simulation and visualization largely focusing on looking into the future to see how well does a building design perform. You'll see examples of that in a minute. And then we also see this production management, co-location, social and managerial methods working in concert to focus the work of a team over the life of the project. So we see this as sort of an operating scheme method for a project team to leverage information, everybody's knowledge, management methods to create the best building that we know how to make every single time on every project. So how do we carry this out, and where are we today in accomplishing this? So I want to share a couple more conceptual frameworks and then go into some examples. Every building has, of course, some design and construction costs, and it also will have some facility maintenance costs, some building operations costs, and some business operations costs. And it has some income from the facility. And all of this can be expressed in monetary terms. It could be expressed in CO2. It could be expressed in human costs. There's many dimensions to the costs as well. So of course, we always try to and should minimize design construction costs, but in the context, of course, of everything else. Because we also want to minimize design construction duration. We want to minimize the operations cost, maximize the income, and usually also extend the life of a facility. So every decision that we make has an impact on some or all of these aspects of a building, and that's where our work is leading to create greater transparency with respect to all of these trade-offs that we do face with every decision, so that we can go through this process in a model-based, more transparent way. In a nutshell, that's what we're trying to accomplish. Of course, it will take a while until we have mined the data, created the computer tools to do all of this, but that is certainly, I think, within reach through the collaboration between academia and industry. Sorry, wrong way. So the key mechanisms I see of creating a high-performing building over the life of the project is, well, the key tasks are defining the user value, then designing, building, and operating the facility. And the key places where I feel we have to connect these processes is in the early design stage, when we need to validate what the user wants and what is feasible. And then we need to carry out throughout the design in a continued evaluation whether the building design is meeting its expected performance. We need to also, of course, bring the building knowledge into design and then carry the design decisions forward through the construction phase. And we need to bring the operation knowledge back into the design and carry it forward. And as you know, many of you that are listening, I'm quite certain, have made great advancements in the last few years in advancing one or the other of these processes. All of this is really in the context of virtual design and construction, building, operating, designing the building, bridge, facility, first in the computer before we actually get it done in real life. So this has several elements, of course, the objectives, the business metrics, project performance metrics that we should meet, and then 3 legs for the project team in terms of the technology, the information, the BIM plus, we sum it up, then the social process of working together, integrated concurrent engineering we call it, and then more formal process management. So BIM is a big deal because it is for the very first time in the history of construction, in the thousands year of history of construction, that we have a tool that combines data and visualization. Because if you think about it, we have always had to enter almost all information twice. We had to create a visualization so that we can talk to each other and we can understand each other. And we had to enter data into engineering and management systems. And this is really the first time that we now have a technology that allows us to do both with one data entry. And that is, of course, has of course huge potential. So that's why I think BIM is a bit different than the introduction of CAD, for example, a few years ago. And personally, I cringe when people say, well, BIM is just another technology. Yes, to some extent it is, but it's really quite a dramatically different technology with a potential that is beyond anything we have seen in the history of construction. So I believe most of you probably have on all of your projects and in your company a strategy for what kind of BIM you will use for what purpose over the life of a project, because there is fundamentally three types of building information models. There's building information models that are predominantly visual, where basically we look at it and the BIM allows us to make sense of what we see more quickly than in 2D drawings, and we can communicate faster, coordinate better. Most projects that I work with use this level of BIM for many tasks over its design and construction phase. The next level is when we harness the information that is in building information models so that we can connect BIMs of different organizations or over the life of different phases, or we can use building information models to automate the analysis for cost, schedule, energy, embodied energy, life cycle, performance, what have you. And then third level is that we can, as I just hinted at, leverage this information to actually automate certain tasks in terms of analysis tasks or creating details or moving the design to fabrication of various tasks that in the past we did manually, but now we can use this 12-cent an hour resource to do. So I see us on a trajectory from construction that I experienced with my father's business, where I would say you can't always see what you get, was sort of past practice, to what you see is what you get is today's practice. And in the future, I think we will have a practice that is what you model is what you get in terms of the performance of a facility. And I think you can see the potential in terms of impact on environment, economy of a project that actually performs as we designed it. And you can also see the potential opportunities from a business perspective for you personally and your organizations if you can actually deliver buildings that perform as we designed them. Today, in many aspects of performance, we are not quite there yet, at least with respect to energy performance. We've seen many cases where even owners that have aspired to create a high-performing building have struggled to get that from the energy perspective. One example on the right is a building, an academic building that should have performed at the level of the stippled line, here the purple line, and the actual performance was quite a bit worse, as you can see. Okay, so let me quickly share an example from one of our member companies, DPR, that you may have seen. It's been presented a few times, but I thought I'll give a quick summary to show you what I think is good practice on projects today in terms of bringing the team together, in terms of leveraging technology, in terms of integrating processes, the aspects that I've highlighted as critical to get it to a high-performing facility. So this is the Sutter Medical Center in Castro Valley, just across the bay here from Stanford. And a couple slides from Digby Christian, who is the project manager for the owner, and then from the design, construction, the IPD team. Basically, Digby from the owner side says, when we typically think design is done and construction starts, there's still a lot of things to be worked out that have a big impact on budget and schedule performance and other performance of projects. So he calls this the Bermuda Triangle of project delivery. I think all of us have been there. So what they are working on is changing that Bermuda Triangle from what is today a pretty high risk effort, because the CDs are basically thrown over the wall to create shop drawings, and then we really realize what's feasible in what time frame for what cost. So because we can now do all of this in the computer, we can create a much better specification of the design that limits the surprises that will come in procurement and fabrication. So we can take a situation from high risk to a situation of low risk. And so their attempt is basically to ask the supply chain to say, well, guarantee certainty of scope, budget, and schedule for the owner if you can find a way to release procurement, fabrication, and installation with zero risk of rework, fully informed by cost and schedule. So basically, the design is validated at least against all of these performance aspects before it is released to become a physical design, meaning before it's fabricated and installed. That, again, we've always tried to do. I think we've all seen that we can do that much better through the use of more collaboration and building information models. So as a result, this medical center will open on budget and on schedule, actually slightly ahead of schedule, and will deliver the whole scope, which for healthcare facilities is not really the normal modus operandi, especially when considered that the scope and budget that was established in conceptual design is really what was delivered. So the design construction, the IPD team, used virtual building tools, but also a number of other techniques, including target costing, process metrics, a big room for the collaboration, design assist processes, and really a virtual company and collaborative planning to achieve this performance. So let me illustrate these. This was one of the, for me, aside from the 12 cent an hour computing, most dramatic images from the last year. When you walk into the trailer, this is what you saw a few months ago. It said, well, target profit 15 million, projected profit 13 million, savings required to maximize profit almost 2 million. This is in the trailer where the owner sits, the design team, the construction team, and it makes it very clear that this team, and this is the first time when on the project team where I felt this really felt like a virtual corporation, where people were working for the success of the project first and then for the success of the company where they came from. And it is quite clear that they can do nothing and just be happy with 13 million profit that they will share, or they can stick their heads together and see how they can come up with another 2 million of savings, which will then go into their pocket. And I believe that's what they did. You see also on the wall a number of metrics that are frequently updated, typically at least weekly, to show everybody where everything is at. So a level of transparency that I typically haven't seen on other projects. This was the somewhat chaotic beginning, but you see a number of smartboards. You see different kinds of models. You see different disciplines. Just getting into finding ways of designing and building the project better. Then collaborative planning sessions, absolutely vital to creating appropriate pool schedules and to getting everybody's buy-in and engagement, everybody's knowledge into the process so that what you schedule is actually what you're going to execute. Then building information model here, basically the sum of all the models, which was rarely used like this, well, except the facade. Of course, there was a facade also. But essentially everything above 1 centimeter was modeled in 3D. They had a long session at the beginning of the project to decide what we are going to model, and then they eventually somebody at the idea said, well, why don't we list what we are not going to model? We might be done faster. And they came up with a list of 5 things, and out of those 5, they still actually modeled 1.5 things. So they modeled almost everything on the project. Benefit of that was just one illustration here, that they could lay out all of the hangers for the pipes and the ducts, of which there's of course many in the hospital, when the metal deck was in, not after the concrete had already been placed. First of all, this layout crew could place about 4 times as many points accurately in a day than before. And then, of course, the installation was much faster of the hangars. And then the installation of all the material below was also much faster because every connection point was already there. And the prefabrication could be very high for these mechanical and electrical and piping pieces. So what you see is what you get, right? This is an illustration of that. It also allowed then fabrication of these elements with minimum material use directly from the 3D model, and it allowed the coordination between, for example, architectural, structural, mechanical, piping elements that again make the project more productive because you could block out the duct penetrations in the drywall before the drywall or the duct was installed, making both trades more productive than the traditional way of punching a hole in the drywall if it goes first, or drywalling around the duct if the duct is already there. So you can see the value of building things in the computer before we actually release it for fabrication, and then the speed you gain in construction by having this integrated model. Another benefit was that the people who led the crews in the field built the project first in the computer for them, for their trade and together. And so when they went into the field to do it, it didn't feel like it was the very first time they saw what they had to build. And you all know from sports, music, etc., how much better we get when we practice a little bit. So here another example of what you see is what you get. You see all the hangers, everything in the model, and then you see them in the field. And they laser scan sometimes daily, certainly at least once a week. They laser scan for sure before an area is closed up, so that you can very quickly compare what should be built against what was actually built. So closing the loop from basically design idea to coordinated set of shop models, then what was actually installed. And they allowed multi-trade prefabrication, where again then of course the field work would go much faster and also higher quality and safer. So you can say this is all good for big companies, but I see some of these practices also in smaller companies. For example, Greg Luth at GPLA here a couple miles away. It's a small structural engineering practice. He, in his practice, designs, details every piece of rebar, for example, for concrete structures with Tekla structures, and basically releases those for fabrication directly. So he has decided that this is actually less risk for him to do than the more traditional structural engineering approach, where he, says, well, this is design intent, now you detailers figure out how it actually goes together. So he likes this method because he says, I can actually really design what really has to be built, and I can know that what's built actually is what I designed and will meet the performance that I need to get. So I imagine that most of you are engaged in these kinds of practices, maybe even more advanced. It would be helpful to me if you can give me feedback as to whether you feel these are indeed best practice on projects today, or you see dramatically better practices. But I wanted to share basically what I see as the starting point from which we can now consider where do we go from here, which is now the next part of the presentation. Because I see leveraging the data, leveraging the 12 cent an hour computing resource, and also the challenges we face in terms of meeting economic and environmental and social sustainability goals. I see that we have to go beyond some of the, in that context, relatively small problems that we deal with on projects today, so that we can, again, produce better projects. And I see automation really as the key method of getting there. In addition to the social integration, I see the automation in terms of leveraging information and the 12 cent an hour resource as really one of the best tools that I can think of. So a famous computer scientist said in 1961, automated execution of processes changes everything. I think you will see what I mean by that through a couple examples that I give in a minute. From a scientific perspective, and that's where I feel the business perspective and the scientific perspective really come together nicely in trying to automate some of the design and construction work and facility operations management work that we all carry out. From a scientific perspective, the value of automation is illustrated in this quote by Don Knuth, a Stanford computer scientist that he made in 1974. Science, which is something that I have to produce so that my dean is happy. Science is knowledge which we understand so well that we can teach it to a computer. And if we don't fully understand something, it is an art to deal with. So there's many things in our projects that are still an art that we learned to deal with through our experience, and we make, obviously the best or good decisions because of that. So since the notion of an algorithm or a computer program provides us with an extremely useful test for the depth of our knowledge about any given subject, the process of going from an art to a science means that we learn how to automate something. So from a scientific perspective, when we try to automate some task, estimating analysis of the building for energy, what have you, we really will uncover the frontier of knowledge of science. And we might be able to advance it, or at least we will understand it better. So from a scientific perspective, automation is a great tool. And then from a business perspective, of course, it's a great tool too, because if we are successful in automating some set of tasks, you have a much better process, faster, more reliable, consistent process to work with. And then you can take benefit from that. So this is where I see tremendous synergy between us on the academic side and then you on the business side. So let me illustrate some examples here. This was really the first example we had in this respect a few years ago, a project we did together with Arup, where one of my PhD students, Forrest Pfleger, spent the summer with Arup, and they had just finished the design of these trusses, roof trusses for a large soccer stadium in the Middle East. And basically, Forrest had been studying optimization methods, and they said, hey, we have a few more weeks before we have to release this project for bidding. Why don't you see what design you would come up with if you use the same tools that we used, but put them into this optimization method that allows to go back and forth between the truss size and the member sizes as many times as necessary to optimize the truss size and the member sizes. So basically he put this computing environment together and came up, as you can see on the right, with a design using a small cluster of 128 computers that was basically about 400 tons less, almost 20% less than the best design the engineers had come up with. And you can see also comparison in terms of effort. The engineers had looked at 39 alternatives, taking 4 hours per alternative, giving a total time of 216 hours. And then with the computer, it took 151 hours in terms of mostly setup time, then running the computer, evaluating the results. We were able to look at 12,800 alternatives, 3 seconds per alternative, and come up with a design that saved $4 million in material costs, which is then the design the engineer took and put out to bid. So on this basis, yeah, sorry, I do have a dog. If I can hear it, I don't know. So on this basis, we thought, wow, this is pretty cool. We should be able to harness this. And we have been working with Beck on a couple case studies where we are applying this to now broader contexts. This particular example is for the conceptual design of housing overseas. where the design team wanted to minimize life cycle cost and minimize carbon footprint. And there was a number of variables to play with in terms of number of buildings, numbers of stories, the building footprint, the parameters to choose in terms of the various dimensions, and the building orientation. There were, of course, a number of things that were given in terms of the floor square foot area and some of the distances to the site perimeter and between buildings. If you look at all of these options, you would have had to look at 1.46 to the power of 11 possible design options, number of design options. Obviously, we'll never look at this many. Well, not never, at least for now. Certainly not with the semi-manual methods we have today. So we were able to, roughly what did the design team do? Just a couple of representative examples. Of course, pick a particular configuration of the buildings and the location on site, analyze them for life cycle impact and cost, came up with a life cycle cost for 30 years of 197 million and 285,000 tons of CO2. They tried a different configuration with somewhat better performance, and a third configuration with, again, somewhat better performance but a little bit different. We can represent each of these methods in terms of their performance on a graph like this, where we see the life cycle impact and life cycle cost on the right. So depending on where a particular performance is, that's where sort of this particular, the green alternative crosses this particular axis. And then the orientation, building parameters, the various dimensions, number of floors, number of buildings. Again, we can basically represent a alternative as a line connecting various points in terms of the particular values of that alternative. Overall, these alternatives. Or we can show these alternatives on a graph like this, where we have carbon footprint and life cycle cost charted, and we can see the trade-off we have between doing a little bit better, being better on carbon but slightly higher on cost, or the other way around. Obviously, this particular option probably you wouldn't choose unless there's some other constraints where this one performs better. But we can, so this is what we see is pretty normal design practice today. We don't really know where exactly in the scheme of possible performance the three that we looked at lie. That, I think, we can only get by using the computer. So what we've done together with Beck Technology is put together all the tools that the design team used in terms of analyzing energy, embodied energy, operational energy, cost, etc., and a building information modeling tool, in this case dProfiler, put them together into an optimization environment that passes the information between these applications and also changes the building information model across the range of possible configurations to come up to see then what leads to the best design. So with this, we can look at thousands of options, and we can trace the good options, which are the ones that are low on lifecycle cost and low on lifecycle impact, shown here by these dark blue lines. So basically, if you follow each of the lines that ends up on the low side here from the many thousands of options that we have looked at and analyzed, or that the computer has looked at and analyzed, we can then see where the good designs come from. We can see that we have two choices in terms of orientation, because all of the dark blue lines cross the orientation line at either this upper area of this particular type of orientation or this orientation. We see we have a bit of a range with respect to building dimension E. We have quite a wide range of possibilities with respect to D. We have a really narrow range with respect to dimension C. We have quite a few possibilities with respect to building length B, a couple with E, with A, and then with respect to number of floors, we don't see any good option coming from 8 floors, mostly 5, 6, or 7 floors. So you can get a pretty good picture in terms of what's driving good performance, at least with respect to these parameters and these performance goals. We can also show these designs, each dot here representing a particular design configuration, on a chart like this, showing the trade-off between carbon footprint and life cycle cost. And you can see that the 3-building, 5-story configurations mostly outperform all of the other configurations in this particular case. And you can see the 3 particular examples that we have looked at charted here. So you can see where they stand in terms of where they fall in terms of the rest of the possible designs. So the design team here found this really quite helpful to see the range of possible performance and the trade-offs they faced. Of course, there's other considerations than the ones we have analyzed here, but still with respect to these goals, we can quite quickly produce, I think, a very good basis for decisions. So if you contrast the two methods, the development of 3 alternatives took about 162 hours total in terms of setup time and then developing each alternative. With the conventional methods and with what we call multidisciplinary optimization methods, MDO, we were able to do it in slightly more time in this case because there was quite a bit of setup time putting these computer programs together. But we were able to look at 21,360 options, 11 seconds per option, and able to save $27 million in lifecycle cost and 10,000 tons in carbon. So I think this is the kind of practice that we can have in the future with the kinds of tools that we are seeing emerging and that we can develop through collaboration with companies. So we're also applying similar methods to the design of construction schedules. This is collaboration with the company CCC, a leading builder in the Middle East, where we looked at, for example, the finishing phase of a very complex university building in Doha, Qatar, for actually Carnegie Mellon. This was really quite high-end finishes, very complex project. It was very difficult for the site team to make good work assignments every day to direct the crews to the right room to do the right thing that would make the crews productive, lead to short overall project duration and cost and low cost. So again, the computer can can work through many options and help us find the best one. This is basically what we did. So we taught the computer about the different types of rooms that there are. Each room consisted of a different sequence of work, which then each of these nodes is a task of one crew for some period of time. That is connected, of course, from a material quantity perspective to the building information model, and from a effort perspective to the construction and productivity database of CCC. With that information, the computer can generate thousands of schedule options for the next week, for tomorrow, for the next month, whatever you like, and you can again chart them in terms of, for example, project duration versus project cost. And you see here a bit of a trade-off in terms of project duration. The schedule with the lowest project duration is not quite the lowest cost schedule, and vice versa. So the project team will have to decide which of these they want to choose. We can also study the effect of the heuristics they were using on site. There were big fights between the superintendents. Some superintendents said, we will achieve lowest cost and fastest construction if we work in as many locations, as many rooms as possible at any given time. So, and others felt we need to just keep everybody as busy as possible. That will give us the best result. Well, we tested these approaches by, again, generating thousands of feasible schedules in the computer and analyzing them. And we find that the heuristic of keeping people as busy as possible was a better heuristic, at least on that job, because when you kept crews busy, meaning they had low idle days, you see the cost tended to be low. That was not the same trend for working in as many locations. Yes, some of the schedules that had low, a good room utilization in terms of crews working in them also had low cost, but others had actually quite high cost. So you might have ended up with that heuristic still picking a schedule that was fairly expensive. So and we are also applying this kind of analysis and simulation to understanding how teams work. We can harness a lot of data from the files that people write to, for example, online collaboration systems like Bentley ProjectWise, and we can then analyze who wrote what information and who used what information when. All of this information is available, so we can create this kind of chart, in this case for a local healthcare project for 1 year, where we saw over 400,000 digital interactions, meaning people writing a file or reading a file. And we can see who consumed whose information most often, who worked together, and who didn't use information that others produced, which may, of course, be appropriate or not. That is for the project team to decide, but at least you get a clear picture of what actually went on from an information and workflow. We can then also analyze over time who was sort of busy. For example, here early on was the general contractor that had the most read and writes of files, and later on it was the architect, as you can see, extremely busy in terms of producing information and also consuming information. So we can start to create these pictures over the life of a project automatically from the data that exists. So with that, we can then start to, over time, learn patterns that we should see or that we should strive to accomplish as we correlate particular information interactions with actual performance. So this was sort of potential where this can go. We can also, of course, create a time slider and look in particular project phases, particular organizations, who used whose information really and who didn't. And the final example I want to share is more at the managerial level, is where we can, in a way, where we can understand how is the project not working overall. We were inspired by this from a project, well, not from a project, from a research effort that Nick Bloom, an economist here at Stanford, and Rob van Reenen, an economist at the London School of Economics, did in studying the performance of the manufacturing industry. They were wondering, what is the best predictor of performance of manufacturing companies? Why do we see such variety in performance? Why are some performing well and others not so well? And they found that good management practices in terms of setting performance goals, tracking it, and actually acting on what you find was the best predictor of successful company performance. So we thought we can implement something like this for our industry, where we built on the framework that they have produced in terms of defining what is good performance tracking. For example, a low score would be measures tracked do not indicate directly if overall business objectives are being met. Tracking is an ad hoc process, and some processes are not tracked at all, versus a good tracking method, which is performance is continuously tracked and communicated both formally and informally to all staff using a range of visual management tools. So we have assessed projects in terms of their management practices, and we've also implemented a process that gives weekly feedback to the project management team on its performance. Because we have seen, again, in manufacturing that more frequent performance monitoring leads to just better performance across the board in many dimensions. So we have worked with 5 project teams for about the last 2 years to measure quality, cost, schedule, organization performance, and correlate that with client satisfaction. So they have filled out weekly surveys based on basically the metrics they said they matter to them in terms of their performance, and we have been able to correlate them. So just a couple examples. On one project, the executive saw just ongoing poor satisfaction with how the meetings were going, and was able to adjust the agenda and improve the performance of the meetings. We have lots of these metrics that we're still in the middle of analyzing, so stay tuned for more detailed insight. But overall, we've seen already that we can better predict client satisfaction. It's less volatile when we have this performance collection and feedback. And we also see some predictors of client satisfaction. For example, when the response latency, commitment reliability, overrun latency are better. Well, the response latency is better, then client satisfaction goes. When response latency goes up, client satisfaction goes down. Commitment reliability goes up, client satisfaction goes up. Overrun latency goes up, client satisfaction goes down. That's in a way intuitive, but now we have data to show this, and we also have data to show that other measures that we thought actually might matter actually don't seem to matter so much. at least not on these projects. We also see correlation between some of these metrics, so if one is going well, then the other one tends to go well as well. So we will continue to do our statistical analysis to help understand what performance metrics are actually truly important in terms of what the client, how happy the client is. So all in all, I hope I've shown you already in the best practices today that teams are accomplishing high-performance buildings through this, through attention to integration. And I think you can see with the research that we have going on, just a couple examples, that with computing methods and management methods, model computing, model management methods, we can even improve upon that. Because I feel that we have to do so, otherwise in a few years we will be unlikely to attract the smart, creative young minds that are currently in high school for whom this way of working is very normal. So I see that we are entering a period of quite different mud that will shape our future leaders. That's what we want to do together with you, to create this new mud that will allow our industry to thrive and our companies and individuals to thrive for the many, many years to come. So if you find any of this interesting, please join us, for example, in June 2021 at the CIFE summer program on breakthrough performance, or at one of our virtual design construction certificate program sessions, or maybe participate with us in research like we have been privileged to do with BECT and CCC, DPR, and many of the other companies, Optima, that shared the examples that I used in this presentation. So thank you for your attention, and happy to answer a few questions in the remaining minutes.
Thanks, Martin. There have been a few questions that have come in. One of them is there's been a lot of discussion in the last few years about the problem of computer models of carbon performance being inaccurate. What has been done to address that project and make these projections more reliable?
So I think the carbon performance, I think that will take quite a bit of effort still to create reliable databases. So what that is one problem that, especially for the US, to my knowledge, we don't really have yet a reliable database that considers, for example, how the energy is produced that is used in, a window manufacturer's plant, right? Which of course has a big impact on the carbon footprint of that window manufacturer. A lot of I've seen better databases in Australia and in Europe, and to some extent we are using some of those databases, which of course we know are not accurate. That's one aspect. The other aspect is that I think we're working on tools to make it easier to estimate the transportation, the activity-based part of this carbon footprint, and then the part, where, let's say, it's a black box where you buy, let's say, a window, and then you have the carbon footprint of the manufacturer. That, of course, goes back into the supply chain of the manufacturer, but we can't really analyze that on a project-by-project basis. And then we still need to, on a project basis, account for, of course, the embodied, the carbon in this window, and then the carbon through the transportation and production process. So I think today we're still putting these tools together to make this analysis better, and we need better databases. I'm not sure, actually, if somebody knows if there is actually a truly concerted effort in North America to create a better database as a starting point. I'd love to actually know that. And then we still need to somehow validate that these are actually good data, right? So we're working on the energy side, which of course is a part of the carbon footprint. We are on a couple projects trying to validate the energy simulation model against the actual data, not only at the level of the whole building, but at the level of the subsystems, so that we actually know that our model is reasonably representative of the actual performance. So this has proven, this is collaboration with Lawrence Berkeley National Lab. This has proven to be really pretty cumbersome, and it's a bit surprising that we as a community haven't put more attention into this, given how many energy simulations I see used and how few examples I see of actual validation of those models against actual performance in terms of assumptions, simplifications, model quality, all of that. So that's an area where I haven't really talked that much in this talk, but that's another area of research in our lab, and I know in other places that we would love to work with people, and or if some of the listeners have an idea of a good project in this area or an effort, we'd love to collaborate with them as well.
Thanks, Martin. We have actually run out of time today, but I will be, this webinar will be up on the Beck Technology website this week. So if anyone would like to go back and reference the information that Martin has provided, it will be available to you at beck-technology.com. Martin, I really appreciate you being part of the webinar and presenting to us a lot of great information for the industry, and we look forward to seeing what CIFE does in the future.
I look forward to working with Beck Technology and many others going forward. It's a lot of fun and very rewarding. Thank you.